Let me enlarge it a bit. They publish structure repair manual, repair design guideline. So it is the format, it is the methodology or principle of the Airbus. They publish this kind of manual, structure repair manual, repair design guideline. This is even better for you because you are able to see, to analyze the repair, to design the repair, to analyze the repair, and all those methodology are given in the manual. So it's very it's easier than other aircraft manufacturer because this Airbus has given you all the information that you need. Okay, let's look at here slowly. Okay, like any other manual, there's a caution, there's a warning, there's a notes. So here you can see the caution. And you can see the purpose of repair design guideline. Okay, you can see the concept here. You can read. Each repair is able to sustain the original design load for static, fatigue, damage tolerance requirement. So I have explained earlier, I believe, about the static, fatigue, and damage tolerance. I have also discussed with you on the design principle. We have safe life, fail safe, and damage tolerant design principle before. Then again, this repair guideline is to ensure that you will be able to sustain the original just design. Original design in terms of static, fatigue, and damage tolerant. And the second sentence, in most cases, only the static requirement need to be met for the repair guideline or secondary structure. Only those will be addressed in this part. So mean that this information in here, all the analysis that given in this manual will cover this mostly on the static requirement. That is most important because that is whatever you have lost, you have to recover back, and you must satisfy the static requirement because other than static, damage tolerant or fatigue, it can come later because the effect of fatigue and damage tolerant will not be immediate. It takes quite some time before you see the effect, the failure regarding fatigue and damage tolerant. That's why if you work on the airline, you may have design, you repair. You have defect on the aircraft, you design the repair, and you go to Airbus, ask for their consent, or ask them to accept your design, approve design, or comment on their design. And most of the time they can come back and say, yes, this is acceptable. However, this approval is not for fatigue and damage tolerant because they will take some time to look at the fatigue and damage tolerant. They analyze the repair against fatigue and damage tolerant, and they can come back later with the inspection interval. So statically, the design is good. However, for fatigue, damage tolerant means for the prolonged application of loads, the failure will be analyzed against the life hours, the life of the aircraft operation, either flight hours or the flight cycle. Okay, so static and stress analysis is performed. So you have to do static and stress analysis to ensure you are able to determine the stresses that in the structure, and then you need to compare with the strength of the material, which is also in the form of stress, and you should always be the stresses that going through the structure should always be less than the material strength otherwise it will fail. So that is one of the condition to accept the design or the repair is to ensure we have enough margin for the stresses. Okay, and you can see the next. There are two main approach in designing static strength capability of the repair. The approach taken depends on how much is known concern the existing load. So in doing stress analysis, you have to determine the load because stress is force over area, force divided by area, or load divided by area. That's why for you to start any analysis, you need to know the loads. So you have to work out the load. Either you get the load from the design manual, stress manual of the aircraft, or you have to work out the load in reverse. We call reverse engineering. If you are the OEM, it's not a problem. If you have any affiliation with OEM, no problem. We can get the stress manual. They can give you all the manual regarding the aircraft structure design. And if you get the manual, you are able to determine, you're able to find those loading at that specific structure area because the manual will give you the information. I was working on C-130 before with Aerod, and we do have the stress manual given by the Air Force, and then it's easier for us as we found damage. We look at the factor safety, whether we still have enough margin to operate the aircraft, or if we have less than the margin, we repair. So it's even easier for us to decide whether to repair, not to repair. It was the first thing you need to do when you see damage on the structure, and then you able to decide whether you need to repair. If you need to repair, and you know what are the thickness of the doubler you need to install for you to be able to get the required factor of safety. So you can see here one, all detail of the applied loading are known. In this case, detailed stress analysis of the part to be repaired results in optimized repair design. This is generally the approach taken by the manufacturer because they have all the information regarding the loads. Number two, which is we always encounter this, no detail of the applied loads are known. In this case, the reverse engineering method may be employed to evaluate the repair static strength capability. So most cases we are in the condition number two, where we are not able to get the detail. We only need to get the detail. However, we still need to look for the loads. The loads have to be developed through reverse engineering methods. I will show you later. Scope and limitations. Scope limitation, the topic in the guideline. Okay, topic presents some guideline which may be used when designing repairs from extruded form section. These guidelines are based on the reverse engineering method. So most of it you will see extruded or form section. There are, I think, around 11 examples given in this manual, and mostly will be showing you how to design extruded section or form section, how to repair them, how to design the repair for extruded and form section, because extruded and form section are the most common form of structure component on the aircraft. And the principle of the design is restoration. These guidelines are based on the restoration of the static strength. So repair, that's why repair is also defined as restore, because what you do in repair is to restore the structure capability. And the resulting repair will be therefore comply with the static strength. So we are focused on static strength, and most of the airline, they do not have the capability to do the damage tolerance and fatigue analysis. And even though they have the capability, they do not have the data, the engineering information to do the uh, detailed analysis or regarding fatigue and damage tolerance. And in order to do the repair, they also give you the guidelines. They give you the principle on the fastener, on the drill, the margin, the sealings, and everything will be given in the manual regarding this. And the repair is considered good regarding all these aspects has been followed without deviation. And the repair here, another thing why we need to have this. If you want to do a repair, you need Airbus approval, you need authority approval. So it's easier for you to get the approval when you follow the guideline given here. You can always refer to the baseline where the concept repair that you develop, where they come from, based on what concept, and you always can go back to this menu and refer back to the pages or the concept repair example number, and that is easier for the Airbus, easier for the authority to review the repair. And then you will see here all the symbol. I'm sure you have seen it before, and you shall be seeing it in your mechanics material. That's why when I taught mechanics material, I always use aircraft as an example, and I always use stress analysis of the aircraft structure, because you need that competency in doing the repair. You may not all of you, okay, may not all of you will be working designing new aircraft structure. However, many of you may be employed by the airlines. I mean, not today, because today the airlines basically is shrinking. When the passenger, when the airlines pick up, when the tourist industry open up, so there will be more people flying, there will be more people operating, and you need more technical services, because structure is always, some of the aircraft parts and components always been damaged, and mainly structure. And then most of you may get a job with the airline as technical service engineer, which end up doing the structure repair. And that's why I always give the example of the airline or the aircraft stress analysis in the mechanics meter, and I focus also on the structure repair manual in detail, and I follow exactly to the manual for you to be able to develop the competency. So you can see here, all the symbol here is something you have seen before. I do not want to go to detail. You can see FBRU, bearing allowable, ultimate, shear, tense shear, ST is okay. It's a crippling, SU shear ultimate, TU tensile ultimate, TY tensile yield. You can see also poison ratio, and all this is something you have seen before, and it's not something. If you think, if you say you have not seen this before, I mean you did not go through the mechanics or material courses. Then there are three factors that you need to be you need to know: safety factor, reserve factor, and margin of safety. So this is three factors that you need to understand, and most importantly, you need to understand the factor of safety, because factor of safety is in the regulation. Factor of safety is in the design requirement, which you need to satisfy for you to design the aircraft structure or to repair the aircraft structure. So let me show you all the three. One, hold on. And this is something that most students have not able to understand this properly. And let me explain this for you not to be like any other student before, which are not able to understand these factors on their own words. You may memorize it, however you not necessarily understand it. So don't memorize, please understand. The level of your study and also the current technology is not about knowledge of memorizing, it's knowledge of understanding and able to apply what you understand. Otherwise, you'll be lost. Okay, here, let me unshare and reshare to you. Okay, you can see here safety factor, reserve factor, margin of safety. What is the focus for you is on the here 1.5. So factor safety must be 1.5. Aircraft design. Okay. Aircraft design requirement is regulation. So by regulation, the factor safety must be 1.5. What does it mean? Okay, let me put a very simple example. Okay, let me put some number first. 150 over 100. Okay, equal 1.5. So let's imagine that you have 150 over 100, you got 1.5. So what is 150? 150 is the ultimate load. Okay. 150 is the ultimate load. So this is ultimate load. What is 100? 100 is limit load. So what is limit? What is ultimate? So this is limit load. So ultimate load is a load which you will never use. This is the design. So this is the design. So mean that you design the structure to 150. You only limit is applied. Applied mean okay. Applied mean the load that you expected in service. So you expected in service 100. If you are doing the design, you expected 100, you design to 150 for you to be able to get 1.5. So that is what I mean. Anyone having problem to understand this? Oh, sir, okay, sir. Okay. So that is what 1.5. So why we need 1.5? Why we need this factor? Okay, why? Because you may have errors in analysis. You may encounter environment which is not expected. You may have manufacturing. Okay, efficiency. So those are covered. We need to cover those. We have to think of that. Because in aviation, nothing is perfect. We cannot accept perfect world. Aviation is not perfect. We have errors. We have something that we are unexpected, environment is something we not expected, and you also have to be concerned on the manufacturing. We cannot expect that everything manufactured as per exactly to the design. It may have some deviation or may have some error in the manufacturing. So those are have to be tackled, have to be handled. That's why we put 1.5. 1.5 means, what does it mean 1.5? 1.5 means 50%. 50% margin in the loading. So it has 50% extra load, extra strength. So if you got 0 means 1, 100 over 100 is 1. 1 means you have 1 to 1. So if you apply the limit load, or apply load, suddenly it just bump into 10% extra, and then you will not get, the structure will fail. But in this situation, if you apply 100 and you may have variation 110, 120, you still have the margin because your maximum design is 150. So the load, unexpected load that occurred can still be handled by the structure because the structure have additional strength. So in the case of reserve factor, it's very simple. Reserve factor is allowable over applied. It's why allowable over applied. So if we need, you can see applied, we can consider also as limit. So when you apply the load, say 100, and the allowable, okay, is 100. So this is reserve factor. Okay. Reserve factor. If you have 100, which is your applied load, when it should not be higher than this. You have to only allow the operation up to 100. Suddenly you have problem. Your aircraft has gone through heavy landing. So the load go to 120. It's something you don't expect and you're not allowed to do. But however, for heavy landing, something you cannot avoid, and then you now have reserve factor of 1.2. As far as factor safety, it's okay, still below 1.5. However, as far as reserve factor, it is positive. It is more than 1. Sorry, it is more than 1. So this is what can happen in aircraft operation, which is 1.5 is something you cannot go lower than this one because ultimate load is what the aircraft are actually designed to. And here in operation, you may have some additional load. Here, if you look at the factor of safety, you only allow 100. Suddenly, something happened, we are not able to maintain 100. You go heavy landing, you have no choice. You have to go around, you have engine failure, you have to go around and come back to the airfield. And because of the fuel, you are unable to offload all the fuel. You have landed heavy and you may have applied the load on the wing by 20% extra. And this 20% extra is allowable, still okay, because as far as margin safety factor, it is still higher than, it still have that 1.5. Margin safety is a reserve factor. Okay, here is 1.2, 1.2 minus 1. You got 0.2. As far as you get it positive more than 0, then you have the margin safety, so the structure is good.